Okay, in the last video, we talked about the difference between 1 over x squared and 1 over the square root of x, right? And we saw that, let me just draw both of these graphs. They both go through the point 1, comma 1. We saw that 1 over x squared almost like dived down towards the x-axis, right? And really got really close to the x-axis really quickly. It's hard for me to draw that there, but sort of get the idea. Versus, so this is like y equals 1 over x squared versus a graph like y equals 1 over root x, which goes to this point, but then just sort of like the denominator grows much more slowly, still eventually going towards the x-axis, but much more slowly, right? And somehow we got a finite area here under this one and an infinite area under the red graph, right? This was finite. This was a convergent integral. But I mean, it really, there is area all the way, forever underneath there. And then, but under the red graph, there was, an infinite amount of area. It diverges. And I did not label the red graph, which is y equals 1 over root x. Okay, so in general, that's why we want to look at these kind of this function, because it always is going to have a horizontal asymptote. So I want to analyze this in general. Before I do that, though, let me think about, I want to give an auxiliary thing, because we're going to be looking at the behavior of this as x goes to infinity. So let's just think about, so first, before we dive into that, let's think about x to the a, the limit as x goes to infinity of x to the a power. And a claim I want to make is that if a is positive, this is certainly going to go to infinity, right? Just like x to the first power will go to infinity, x squared will go to infinity, even x to the 0.2 power. Because the exponent's positive, that means there's an x in the numerator, versus if a is less than 0, right? What happens if a is less than 0? That's like if a was, for example, -1 right here. Just think about this, e.g. a equals -1, then this is really 1 over x. And as x gets large, now if you have a negative exponent here, the x is in the denominator. That's the point. X is in the denominator, and that means this goes to 0. So that's the first fact we're gonna need to use later. So just to think about that, like it's basically, you just think whether x ends up in the numerator or the denominator. I'll just write that here. Or denominator. That really determines what's going to happen to x to a fixed power as x goes to infinity, right? Okay, now with this property established, we can tackle the integral itself. So it's a little bit abstract, but let's just do it. So, if we're going to look at the integral from 1 to infinity, 1 over x to the p dx, we know by definition that that's the limit as x goes to positive infinity of the integral, not x, b, the right-hand endpoint of the integral, right, is what's going to infinity. 1 to b, x to the minus p dx. Okay, so let's look at this integral for a second. In fact, let me drop the limit for a second and just tackle this, right? Just so I don't have to keep writing the limit. So we know the antiderivative of x to the minus p. So let's think about this. We add 1 to the power, right? So we have x to the minus p plus 1. And then we divide by that. Okay, so it looks something like that, right? Let me write that a little better. 1 over minus p plus 1. But one thing we have to notice is that this doesn't work when p is 1, right? This only works if p is not 1. Because if p is 1, then we have a problem there. We're dividing by 0, right? Again, let me see if I can just really write that better. I just feel like it's not as clear looking as I want it to be. Minus p plus 1. Okay. So, right, we don't want to divide by 0. So we have to separate that case. So we're going to save the p equals 1 case and do that separately. That's the case when the power rule doesn't work, kind of like when we can't use the power rule on x to the minus 1 power, because we add 1, we get x to the 0 power over 0. Doesn't work. That's the natural log case, right? Okay, so that's the first comment I want to make. And then, but let's just go ahead and do this in this case. By the way, I can rewrite this as 1 over 1 minus p. I think that's a little bit easier. And then we're going to plug in b and we're going to plug in 1. So it's b to the 1 minus p minus 1 to the 1 minus p, which is just 1. All right, and now in order to think about, so now we need to take the limit of this as b goes to infinity, right? And so it really comes down to this expression, the b to the 1 minus p. So the limit, let's just write it this way. The integral from 1 to infinity of 1 over x to the p dx is 1 over 1 minus p times the limit as b goes to infinity of b to the 1 minus p. And then there's a minus 1 there. It's kind of like that, I guess. Okay, so this is the thing we need to evaluate, this expression right here. And that's why that's where the limit up above is going to help. Maybe I should have probably made this, if I'd been a little smarter, I probably would have made this a b. So just think about that being a b, because that's really what we're doing. And now and then our a is 1 minus p, right? So this right here, there's two possibilities, right? If 1 minus p is positive, so that's the exponent. If the exponent's positive, then this is going to blow up. It's going to be a positive number to a positive power, and it's going to get bigger and bigger as this number gets bigger and bigger. So that's going to be plus infinity if 1 minus p is positive. And it's going to be 0, right? If 1 minus p is negative, then it's like the b's in the denominator, like we were saying above. So it's 0 if 1 minus p is less than 0. By the way, there's a third case, 1 minus p equals 0. But notice that's exactly the case here, right? 1 minus p equals 0 is the same as p equals 1, which is what we're sort of saying we have to deal with separately. So it actually is kind of all fitting together. And so this expression, so the whole thing, basically, what I can say is, if we just want to kind of go from here, this thing, there's two possibilities, right? This is the same as p is less than 1, and this is the same as p is greater than 1. And in this case, in the p is less than 1 case, we get infinity here, this integral diverges, right? So basically, the integral diverges if p is less than 1, and it converges because we actually get a number here, right? We get 0. Actually, this is 0. We actually get like minus 1 over 1 minus p, or, it's an actual value. But I'm just really asking whether it converges or not. So it converges if p is greater than 1. And actually that fits, right? We did cases. We did the case p equals a half, right? The 1 over square root. And we also did the case p equals 2 when we did 1 over x squared. And so that actually fits those two cases. And what we're saying is that 1 is actually the tipping point. But this is the big result. In fact, maybe I should write it. Instead of doing this, maybe I should just copy this integral down here. The integral from 1 to infinity, 1 over x to the p dx. Two possibilities there, although we still have the last possibility we have to think about. So what if p equals 1? Then we have the integral from 1 to infinity of 1 over x. Still can't draw an infinity sign. Okay, but this is interesting, right? This is actually, well, I'm just going to write the definition like I normally do. I have trouble every time I draw an infinity sign. So integral from 1 to b, and this is the natural log, right? It's ln x from 1 to b, which is the limit as b goes to infinity. If we plug in b and we plug in 1, well, this is a natural log of 1 is actually 0, so it doesn't matter. But what about natural log of b as b goes to infinity? Well, do you know what natural log does as b gets large, as the input gets large? Let's just think down here. Natural log of e to the 10th is 10. Natural log of e to the 1/1,000,000th, or however many zeros that is however many zeros that is. I don't know if it's the same number, but you get the idea. This does get large. It takes a long time. Natural log grows really slowly. E to the millionth power is a huge, that might be 10 millionth power. It might be the 10 millionth power. Doesn't matter. Anyways, this is a huge, huge, huge number. And the natural log is only that number, which is not nearly as huge, but it still means the natural log grows without bound, right? So natural log does go to infinity. Just putting this as an aside. So this does go to infinity. So the integral of 1 over x dx, I'm just going to redraw my infinities every time, diverges. Okay, so in fact, the p equals 1 case also diverges. So if I go up here, I can actually put less than or equal to 1 right there. Okay. And so now we have, this is the big statement, basically. But that's interesting, right? So we saw that 1 over root x, right? Like if we had 1 over root x here, the integral will diverge. If we have 1 over x squared here, it will converge. But that means weirder things too. Like if you have 1.0001, that's actually in this case. So something like, so just kind of weird, but this is really the tipping point of it all. The integral from 1 to infinity of 1 over x dx diverges, but the integral from 1 to infinity of 1 over x to the 1.00001. And if you graph those, they do not look much different. In fact, it's really hard to see the difference between these two functions. But this one converges. So maybe a big final point here is that intuition is hard to come by. This is non-intuitive. This whole stuff, all of this is non-intuitive. But it has something to do with how quickly these graphs are approaching the x-axis, and that somehow 1 over x is just not quite quick enough. This is not approaching the x-axis quite quickly enough as x gets large. And this is just a tiny bit more quickly because this denominator is growing just a tiny bit faster than this is. And somehow this is going, this function is going to 0 just fast enough to choke off a finite area underneath it. So it's okay. It's not intuitive, it's okay, but this is what the results of the math tells us. Okay, so I will stop there.